Why is there a blue glow surrounding nuclear reactors? There are few plausible explanations as to why the light in the water is blue. One reason is the atoms in the water become excited by the particle shock wave and then de-excite, emitting blue light. The other reason is the number of photons emitted by such a charged particle is inversely proportional to wavelength. This means that more photons are being emitted with shorter wavelengths, thereby tilting the spectrum to the blue side. In this podcast, we'll explore Cherenkov radiation. In 1934, while working under S.I. Vavilov, a Soviet physicist known for his works in luminescence, Pavel Cherenkov observed this emission of blue light from a container of water that was subjected to radioactive bombardment. His colleagues and fellow Soviet physicists, Ilya Frank and Igor Tamm, provided the theoretical explanation of this effect. This occurs when charged subatomic particles move through a dielectric medium faster than the speed of light in that medium. Little did they know that this discovery would change the way we study the universe. In 1958, Pavel Cherenkov, Ilya Frank, and Igor Tamm were jointly awarded the Nobel Prize in Physics for the discovery of the Cherenkov effect and its explanation. How has this blue glow expanded our understanding of the universe? SciFinder is the first choice for scientific research. SciFinder provides researchers and scientists with easy access to the highest quality and most comprehensive scientific information available, including CAS registry, the gold standard for chemical substance information. Let's see what SciFinder reveals by entering Cherenkov radiation as the research topic. SciFinder allows you the opportunity to access published scientific literature from the past 100+ years. After reviewing our initial reference set, we discover a 1951 reference describing a Cherenkov radiation detection method via H2O utilizing a photomultiplier tube. The light emission was measured as an effect of depth of the water, orientation of the counter with respect to the vertical, and the discriminator bias. For more than 75 years, the vacuum-based photomultiplier tubes, or PMTs, have been the standard. PMTs basically are very sensitive light detectors. They are typically used in conjunction with scintillators to detect nuclear and particle radiation. Here are a few more recent articles covering the uses of silicon-based photomultiplier detectors, or silicon PMs. Is the silicon photomultiplier the standard, or is it the most recent trend? To speed up the research and discovery process, index terms, located near the bottom of the abstract, are hyperlinked to retrieve documents associated with photomultipliers. The linked text retrieves 2,362 references associated with photomultipliers. This particular reference from the Stefan Meyer Institute in Vienna, Austria, discusses their evaluation of several brands of silicon PMs when used in conjunction with a scintillating fiber and Cherenkov radiation. This provided a better understanding of the timing performance, compactness, and low cost compared to traditional PMTs. Does this mean silicon PMs are the next step to enhancing photon counting and detecting Cherenkov radiation? Are silicon PMs giving the traditional PMT some competition? A silicon PM provides a more robust and higher performance alternative to the traditional PMT. Silicon PMs provide a more sensitive, smaller, lower power, and better performing optical detector. Silicon PMs are attractive detectors for ring imaging Cherenkov counters inside large magnetic spectrometers because of their insensitivity to magnetic fields. These researchers from the University of Maribor, Slovenia, explored these new photon detectors in a cosmic ray setup. The conclusions that were drawn indicate a strong promise for inclusion in future ring imaging Cherenkov detectors. This research from 2009 could provide useful in future endeavors. SciFinder allows you the opportunity to tag or label references. You can accomplish this either with individual references or when grouped as a set. Consider this an opportunity to jot down critical messages or thought tags. These can include descriptive terms or keywords that can facilitate grouping and recall of references at a later point. Traditional photomultiplier tubes may remain the preferred method of photon detection. That can be demonstrated by a monumental undertaking nearing completion in the South Pole. IceCube, a telescope under construction in deep Antarctic ice by deploying thousands of spherical optical sensors. Let's learn more of this polar marvel, IceCube. When we use IceCube as our research topic, the first reference retrieved is what we have been exploring, photomultipliers. The IceCube will search for dark matter, which could lead researchers to a new understanding of the highest energy particles in nature. The next steps in discovering the wonders of the universe is occurring in the Antarctic. As the world's largest neutrino telescope in the world, it is scheduled for completion in 2010-2011. Another reference is located, which is a review covering the prospects of massive neutrino telescopes, such as IceCube, and the role they will play in the research for particle dark matter. What is dark matter? Dark matter is inferred to exist from gravitational effects on visible matter and background radiation, but is undetectable by emitted or scattered electromagnetic radiation. Understanding dark matter is important to understanding the size, shape, and future of the universe. The amount of dark matter in the universe will determine if the universe is continually expanding until it decides to collapse or flatten, or expanding until it reaches a sort of equilibrium. It is a marvel how an observation and simple technology from more than 75 years ago still play a crucial role in the field of particle physics and expanding our understanding of the universe. SciFinder plays a crucial role in today's research process. Your research is too important not to use SciFinder. To learn more about SciFinder, visit www.cas.org. SciFinder provides easy access to information in the CAS databases and can help you explore all of the published scientific literature related to your research topic. Get current, get informed, get SciFinder.